Okay, I'm just going to work out the problems from the AP probability packet. The probability of obtaining a head when a certain coin is flipped is about 0.65. Interesting. Weird coin. Which of the following is closest to the probability that heads would be obtained 15 or fewer times when the coin is flipped 25 times? So we're saying out of 25 times, we want 15 or fewer heads. So I'm thinking this is probably binomial because I don't want exactly 15 and I need to kind of accumulate them. So this is going to be a binomial CDF problem. So I want 15 or fewer times. So I could do binomial for each of these, or I could just do binomial CDF. So what I'm saying is I want binomial CDF. And I want out of 25, there's a 0.65 chance of getting heads, and I want 15, up to 15 heads. Okay, and this will give me my answer. So I knew it was binomial because I was thinking, okay, if I flipped 25 times and I want 15 heads, that's 0.65, and I want it 15 times. And then the rest, I want not heads, which would be, if there's 25 times 10. And then it could be in any order. Okay, and then I have to figure out how many different ways I could make that happen. Now this is exactly 15, and this says 15 or fewer. So that means I would have to add the same thing for 14, and then et cetera, which is what's going on with the binomial CDF. So then I go ahead and I type that in. Second vars, binomial CDF. And I get 0.369, which is 0.37. Okay. In a certain school, 17% of the students are enrolled in psychology, 28% are in foreign language, and 32% are in either psychology or foreign language or both. So this has overlap. And when I add all three of these up, I get 32. What is the probability that a student chosen at random will be enrolled in both a foreign language and a psychology course? So I don't know what this is. So you have two options. You can think about it in the Venn diagram way, where I know that if this is psych and this is foreign language, and psych is 17 total, and foreign language is 28 total, I know that this circle is going to be 0.17 total. So this little area here is 0.17 minus x. And this little area here is 0.28 minus x. And then I would just add all of these up, and they should equal 0.32. And so these cancel out. And I get 45 minus x equals 0.32, and then I just need to solve for x. Okay, the other option is to think of like the formula. The probability of psych or foreign language should be the probability of psych plus the probability of foreign language minus the probability of both. Okay, so we know that or is 32%. And so 0.32 should be the probability of psych, which is 17, plus the probability of foreign language, which is 28, minus both, and that's what we're looking for. And so they wind up being the same thing. 0.32 equals 0.45 minus x. What is this? Negative 0.13. And so x is 0.13, so that's D. Okay, they're the same thing. All right. The number of points X scored in a game has the probability distribution below. The number of points obtained in one game is independent of the number of points obtained in a second game. Okay. When the game is played twice, the sum of the number of points for both games could be 0, 1, 2, 3, or 4. So it's like saying that 0 would be if you got 0 and then 0. 1 would be if you got 0 and then 1. Or 1 and then 0. 2 would be 2 and then 0, 0 and then 2, 1 and 1. Three would be 1 and 2 and 2 and 1. That's kind of it. And 4 would be 2 and 2. Okay. Because it's when the game is played twice. These are the possible sums. So it could either be 0, 1, 2, 3, or 4. For which value of y will the probability be the greatest? So which of these will it be the greatest for? I'm guessing it's 2 because there are 3 different options here. So I'm saying it could be 2 and then 0, so that's 0.3 times 0.4. Or 0 and then 2, so that's 0.4 times 0.3. Or 1 and 1, which is 0.3 times 0.3. And I think because this one has the most options, it's automatically going to be the highest. Yeah, there's really no way, because this is kind of, this is 0.16, but this is 0.12 plus 0.12 plus 0.09, so that's 0.33. So this one's going to be like way higher. So I think that number 2 should be the greatest, because there's 3 different ways to get 2. You could roll a 2 and then a 0, or a 0 and then a 2, or a 1 and then a 1. And every time we say or, we're adding probability. We could actually calculate all of these if we wanted to. 0 and then 1, or 1 and then 0. Yeah, so these are all going to be smaller. Okay. For flights from a particular airport in January, there is a 30% chance of a flight being delayed because of icy weather. If a flight is delayed because of icy weather, there's a 10% chance that the flight will also be delayed because of a mechanical problem. If a flight is not delayed because of icy weather, so this is like, okay, if this, then that. If this, then that. So this I'm going to organize better with a tree. So there's a 30% chance of flight of being delayed because of icy weather. So it's like there's icy weather. So there's a 30% chance of icy delay, which means there's a 70% chance it doesn't get delayed for ice. There's a 10% chance the flight will also be delayed because of mechanical problems if it's icy. So mechanic delay. No mechanic delay. So there's a 10% chance of also mechanic delay, 90% chance of none. If a flight is not delayed because of icy weather, there's a 5% chance that it will be delayed because of a mechanical problem. So this is a mechanic delay, which is 5% chance. Okay, and so now I'm just going to find these probabilities to finish off my tree, which organizes my thoughts. This is 0.03. This is then 0.27, I think, and then this is 0.035. So then this is 0.665. I'll check that one. I'm just multiplying across because I'm saying no icy delay and no mechanic delay, so those have to go together. Okay, so the question is, what is the probability, if one flight is selected at random, what is the probability that the flight selected will have at least one of the 2 types of delays? So either mechanic or icy delay. So here's a mechanic delay, at least one. So here's one. Icy delay, this one also has one. And this one has both. So all three of these. So 0.03 or 0.27 or 0.035, which should be 0.335. So that's B. Okay, 90% of people who have a particular disease will have a positive result on a given diagnostic test. 90% of the people who do not have the disease will have a negative result on this test. So they either have the disease or don't. And then 90% of the people who have the disease will have a positive result. And then 90% of the people who do not have the disease will have a negative result. Oops, so this is 0.9, negative result. If 5% of a certain population has the disease, 95% does not, what percent of the population would test positive? So we're just looking for this positive zone. Okay. I don't know why I did that. I could do that in my head. So we're looking for positive. So here's positive and here's positive. 14% will test positive. Even though only 4.5% will actually test positive and have the disease. 14% will test positive. So you'll have these like 9.5%, which are false positives. They're positive even though they don't have the disease. Okay, a police officer is using a radar device to check motorist speeds. Prior to beginning the speed check, the officer estimates that 40% of motorists will be driving more than 5 miles per hour over the speed limit. So 40% are speeding. Assuming that the police officer's estimate is correct, what is the probability that among 4 randomly selected motorists, at least one is speeding, is more than 5 miles over the speed limit? So there's a 40% chance of speeding. So not speeding is 60% chance. Okay, 1 minus 0.40 is 60. And this 5 is not a relevant number. It's just saying that they're speeding. And so among 4 randomly selected, we want at least one to be speeding. So at least one means 1 or 2 or 3 or 4 in any order. So the only thing we don't want is everything except no speeding. So we're gonna, at least one roll means we need to think about what's the one thing we don't want, and that would be none of these. So if these are all not speeding, they're all 0.6s. So it's 1 minus 0.6 to the 4th. .8704. D. Okay. Mating eagle pairs typically have 2 baby eagles called eaglets. When there are 2 eaglets, the parents always feed the older eaglet until it has had its fill, and then they feed the younger eaglet. This results in an unequal chance of survival for the 2 eaglets. Suppose that the older eaglet has a 50% chance of survival. Again, a tree. If the older eaglet survives, I know it's a tree because I'm seeing all these ifs, which means it's dependent on each other, which means a tree will help. So if the older eaglet survives, so it's based off the older survives, older dies. That's depressing. So suppose that the older eaglet has a 50% chance of survival. 50-50. If the older eaglet survives, the younger eaglet has a 10% chance of survival. So young survives. And it's only a 10% chance, so the young dies, there's a 90% chance it dies if the older one survives. If the older eaglet does not survive, then the younger one has a 30% chance of survival. So I finish my tree by multiplying. And now, which of the following shows the probability distribution? 0 means that none survive because X represents the number of eaglets that survive. So none surviving would be them both dying. Older dies and younger dies, so it should be 35%. Oh, which is C. Okay, and I can check the rest. Both surviving, older survives and younger survives is 5%. And then one surviving, meaning this one or this one. Because these ones, this one the young survives, that's one surviving. And this one the older survives, that's one surviving. 0.60. Okay, that's the multiple choice. And now the free response. Okay, schools in a certain state receive funding based on the number of students who attend the school. To determine the number of students who attend a school, one school day is selected at random, and the number of students in attendance that day is counted and used for funding purposes. The daily number of absences at high school A in the state is approximately normally distributed with a mean of 130, so it's normal, and a standard deviation of 10. If more than 145 students are absent on the day the attendance count is taken, then the school will lose some of its state funding the subsequent year, the next year. Approximately, what is the probability that high school A will lose some funding? Well, we know it's normally distributed, and we're talking about a single day, so that's just a basic population normal distribution, where it says the mean is 130, and the standard deviation is 10. And this is number absent. And so they're saying if more than 145 are absent, they will lose funding. So I need to figure out how many standard deviations away from the mean I am. So I'm 1.5 standard deviations away from the mean, and then I need to calculate over that. So over this, it's 0.0668. So there is about a 7% probability, so 6.68% probability that they will lose funding. Okay. The Principals Association in the state suggests that instead of choosing one day at random, the state should choose 3 days at random. With the suggested plan, high school A would lose some of its state funding the subsequent year if the mean of those 3 days is greater than 145. Would high school A be more likely, less likely, or equally likely to lose funding using the suggested plan compared to the plan in Part A? Well, now what's happening is that instead of having just one single day, now we're looking at little samples of size 3, and each sample average will be on this curve. So this is a sampling distribution. And so when I look at the average of 3 days, instead of just looking at individual days, what's going to happen is the standard deviation is going to change. It's going to decrease because I'm looking at averages, and so they vary less. When you look at a sample of 3 people on that average, it should vary less than 1 person to 1 person. So we should make our curve here where there's 130 in the middle. And then my standard deviation, the new standard deviation, is going to be, oh, that was the wrong symbol. Should be this. Okay, and it will be, the original standard deviation was 10 over the square root of 3. So my standard deviation changed to 5.77. So this is like 135.7, etc., etc. And so if I 141.54. So now we're somewhere out here, more than 2 standard deviations away from the mean, as opposed to being 1.5. Now technically I should check conditions to make sure that I can make this normal curve. So 1, is it big enough? It's not big enough, but they stated that the population is nearly normal, or is approximately normal. We can assume random days because said so. So stated random selection. And then of days. And then we can assume independence. Especially because 3 is less than 10% of all the days in a given year. So we can make this normal curve, which means we can then find our z-score using this new standard deviation, and then normal CDF that. Oh, technically it's a t-score. .5996. Okay, and now we're gonna go second vars, TCDF, 2.5996 up to 999. Oh, and the DF will be 2. So that's 0.0607. So that probability did decrease. Technically, my curve is a little bit wider now since I'm using a t-distribution. But 0.0607 is my now my new probability. So probability decreases. Less likely. All right, so a typical school week consists of 5 days, Monday through Friday, obviously. The principal at High School A believes that the number of absences tends to be greater on Mondays and Fridays. If one school day is chosen at random from each of 3 typical school weeks, what is the probability that none of the 3 days chosen is a Tuesday, Wednesday, or Thursday? So we have these 3 days, and none of them are Tuesday, Wednesday, or Thursday. So we're assuming that every day is equally likely, so there's 5 days. There's a 1 out of 5 chance for each of these days. And we're saying that it's not Tuesday, Wednesday, or Thursday, meaning this is Monday or Wednesday. And this is also Monday or Wednesday. And this is also Monday or Wednesday. And there's a 1 out of 5 chance that it's Monday, and a 1 out of 5 chance it's Wednesday, meaning a 2 out of 5 chance it's Monday or Wednesday. Oh, sorry, not Wednesday, Friday. I apologize. Still a 2 out of 5 chance though. 2 days out of the 5. And so all of them have to be Monday or Friday. So I'm going to multiply. So it's 0.064. So there's a 6% chance, another 6%, a 6% chance that they get all Mondays and Fridays, which are their low attendance days, high absence days. So interesting. Okay. Number 2. 11 sales representatives, 7 men and 4 women at a small company wanted to attend a national convention. There were only enough travel funds to send 3 people. The manager selected 3 people to attend and stated that the people were selected at random. The 3 people selected were all women. There were concerns that no men were selected. Calculate the probability of randomly selecting 3 people from this group of 11 sales representatives will result in selecting 3 women. So calculate the probability that it's women, women, women. And there are 11 sales reps. So this is a small population to pick from. So I'm going to use fractions because, you know, N is not less than 10% of the population. The population's only 11 and we're picking 3. So I need to use fractions and consider that every time I pick one, that person is out of the pile. I don't get to put them back. So if it's a woman, there's a 4 out of 11 chance of getting a woman the first time. Then I take that woman out. There's 3 women left out of 10. And then there's 2 out of 9. And I multiply that guy. Oops. 4 divided by 11, 3 divided by 10, 2 over 9. There's a 2% chance that that could have happened if he actually selected it randomly. So based on your answer to part A, is there reason to doubt the manager's claim that the 3 people were selected at random? Do men have reason to claim discrimination here? Why, yes. If selecting at random, there is only a 2% chance of getting all women. So it was nearly impossible. Less than 5% chance. Usually we use 5% to get all women randomly. And yet he did. That's what we say. Right? Like, I doubt that he actually selected randomly. He probably picked a little bit, or, you know, thought he was doing randomly, just like humans do, but we know that we can't actually select things randomly. We need to use some sort of system. Okay, calculate the probability of selecting at least 1 man. So that's everything except all women. So there is a 76, a 97.6% chance of at least 1 man. So there was pretty much an assurance that at least 1 guy was going to go. But they didn't get at least 1 guy, so something was wrong. Okay. The last one here, number 3. A shopping mall has 3 automated teller machines. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. The table shows the probability distribution of x. Complete the table above, justify your work. So it's missing this bit. I know that this should be all of the possible number of ATMs working, which means this should add up to 100%. Right now it adds up to 0.56, if I did that correctly. Which means this leftover bit is 0.44. So it looks like there are 3 ATMs total, 3 automated teller machines, ATMs, and so the probability that 2 are working is 44%. What is the probability that at least 1 ATM is working when the mall opens? At least 1 means 1 or more. So 1 working is 0.21, or 2 working, or 3 working. So I just add all those up, and I should get 0.90. You could also do everything except none working. Everything except none working. So the probability that none are working, which is 1 minus 0.10, which is 0.90. So you get the same no matter how you do your work. Okay. What is the probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working? So the probability that all 3 are working, given at least 1 works. So my denominator is at least 1 works. At least 1 we just did. At least 1 works is 0.90. Given that at least 1 works, what's the probability that all 3 work? So, and at least 1 works, those are basically the same thing. So that all 3 work is 25. .277. 8. Okay, so given that at least 1 works, where these intersect is just at all 3 working. Because given that at least 1 works, so that's our denominators, all 3 of those, what's the probability that all 3 work? And there's the intersection right here. If there are 10 malls that follow this distribution and are independent of one another, what is the probability that exactly 5 of the malls have all 3 ATMs working? So out of 10 malls, I want 5 to have 3 ATMs working. So I could think of this as dashes, where 5 of them have 3 working. 1, 2, 3, 4, 5. So 5 of them have 3 working, exactly 5. So that means that these ones don't have 3 working, which is everything else. It could be 2, it could be 1, I don't care. Anything but 3 working. But it doesn't have to be the first 5 malls. It could be the last 5. It could be that it's the first one and the last 4. There's like a ton of different ways to make that happen. So we need to calculate 10, how many different ways we can make that happen. So it's 10, choose 5 ways to make 5 all 3 working and 5 not all 3 working. .0584. If there are 10 malls that follow this distribution and are independent of one another, what is the probability that at least 5 of the malls have all 3 ATMs working? So now I want at least 5, so 5 or more. So I don't want exactly 5. I want this, or with 6, or 7, or 8. So I want to accumulate out of 10, all 3 working, Now here, I want the right-hand side, but the calculator can't give me that side. So I want everything except up to 4. And that gives me 0.0781. And that's it for our probability packet.